Hello, I'm Kenji Tojo, an MS student at the University of Tokyo. Today I'm going to present our research on stylistic rendering of neural radiance fields. This is joint work with Nobuyuki Umetani at the University of Tokyo. The state-of-the-art computer vision allows us to synthesize arbitrary viewing angles from sparse object capture like a set of photos. The key technology behind these impressive results is a trainable scene representation called neural radiance fields. The neural radiance field is a volumetric representation encoding a 3D scene using two continuous fields. The first is a density field, which maps a 3D point to the scalar volume opacity at the position. Another is a radiance field, which takes 5D input consisting of 3D position and 2D viewing direction and outputs RGB color. Given these fields an arbitrary camera pose, each pixel's RGB value is computed via the volume rendering for the corresponding camera ray. This volumetric representation has achieved state-of-the-art performance in 3D learning tasks. More recently, the volumetric radiance fields have been applied to a broader range of content creation tasks, especially photorealistic contents. For example, they are used for 3D array realistic image generation and realistic surface appearance modeling and editing. However, photorealism is not the only goal of content creation. Computer graphics researchers have presented algorithms to reproduce various artistic styles to extend the limit of artist expression. These techniques are called non-photorealistic rendering, or NPR in short. Previous NPR methods have considered various input representations such as meshes, 2D images, and scalar fields like a CT-scanned volume. However, volumetric radiance fields do not fall into these traditionally considered representations. So it is unclear how to perform NPR on the NERF representation. The general goal of our research is the NPR of NERF, but this presentation focuses on the style called artistic posterization. Artistic posterization, or just posterization, is a technique that produces an abstract representation of continuous images using constant or flat color regions. Because there is no correct answer to the stylization, we'd also like to consider ways to edit the colors of the result. Now let me briefly introduce the potential approaches to this problem. Adapting the neural style transfer could synthesize the posterization style. However, it often requires dedicated training procedures or additional neural nets that slow down the training and inference. Neural net training is beyond the scope of this presentation, and we consider the pre-trained volumetric radiance field as static data. Shader-based methods reproduce cartoon-like styles using a tailor-made lighting model known as a cell shader. However, they typically rely on watertight surface geometry or detailed lighting conditions, which are not readily available for visually supervised neural representations. On the other hand, palette-based methods directly work on RGB data of, for example, images and videos. Due to the generality of this method, we focus on extending the palette-based approach to the volumetric radiance fields. So let's first see how the existing palette-based methods work. Palette-based methods first extract a small set of characteristic colors from the input image and use it as a color palette for the stylization. A simple and efficient palette extraction algorithm by Tan et al. Uses the RGB space geometry. It computes the convex hull of the RGB data, iteratively simplifies it, and obtains palette colors as the simplified hull's vertices. In the palette-based posterization, the extracted palette is used to fill each flat color region. This means the resulting colors are written as a linear blend of palette colors. A nice thing about this is the result is naturally decomposed into additive color layers. This allows users to retouch the chromatic appearance by modifying a few palette colors. This is the palette-based posterization, and let's consider using this method with radiance fields. The first step is palette extraction, and of course we can compute a palette for a radiance field from an example rendering. However, this palette from image approach can fail to deal with view dependence. Because the radiance field encodes multiple views with complex physical effects such as highlight and occlusion, different views can lead to significantly different set of palette colors. In searching for an acceptable palette through trial and error with different camera poses is tedious and non-trivial manual work. Or you could extract a palette for each rendered frame. However, using different palettes frame by frame leads to temporal incoherence when used for posterization. And of course, having many palettes complicates the color editing. In this presentation, we took another approach. We pre-compute a palette that covers the radiance field's full 5D spatial directional color distribution, and we use it at runtime to stylize renderings. To do this, we generate color samples we call radiance samples by evaluating the radiance field. This approach allows us to capture the world space color distribution without indirectly specifying camera poses. Now let's dive into the specifics of our palette pre-computation algorithm. Although it first looks straightforward, this approach has two problems we need to solve. The first one is, of course, the way to evaluate problem. We must determine the set of input 5D points passed to the radiance field. In addition, we found that trained radiance fields have significant noise invisible due to volumetric occlusion, so we must deal with such noise to obtain a high-quality palette. To generate 5D points, we basically use a regular sampling from the domain. For each position on a regular 3D grid, we again regularly sample directions to generate a 5D vector. However, this quickly produces an intractable amount of points due to the curse of dimensionality. So we leverage the sparsity of the density field and reduce spatial sampling points by thresholding the density. Then the directional domain is regularly sampled at each location. And another issue is the noise in trained radiance fields. To understand this, let's take a close look at the directional domain around the blue point. This is the heat map of volume occlusion visualized using the cylindrical projection. A brighter color means more visible, and a darker means more occluded. Radiance fields typically have regions occluded by the volume. In this case, we can see the dark silhouette of the hot dog. And this is the RGB radiance output around the point. As you can see, occluded regions have irrelevant colors like pink or blue. This is because such regions do not contribute to the image-based loss function during training and can stay unoptimized until the training has converged. Unfortunately, directly fitting a convex hull to such noisy RGB data results in a palette with extreme colors, leading to low-quality stylization results. We address this issue by weighting each radiance sample by their volumetric visibility. To explain our visibility formulation, let's consider 3D points in a volume like X and Y. And sigma is the NERF's density field, outputting a volume density at each 3D location. Another volumetric quantity we use is transmittance between X and Y, which is mathematically defined like this. It looks a bit complicated, but what it's measuring is how much light intensity is attenuated while passing through the volume between X and Y. Remember, we want to define the weight of each spatial directional input to the radiance field, a pair of X and viewing direction D. Conceptually, we define this weight as the intensity of light at X and D seen from an infinitely distant observer. In summary, our visibility weight is the product of density at X and the transmittance between X and X minus D times infinity. So how do we use this visibility weight to eliminate the effects of noise? Given radiance samples, we first compute a histogram of visibility in RGB space, and we then create the representative data points via the k-means weighted by volumetric visibility. Because this step is not to obtain the final palette, we control the cluster number k relatively large, which is about 20 to 50. The representative cluster centers are then passed to the convex hull method to get the final palette. This two-step procedure, k-means and then convex hull, allows us to obtain vibrant colors as a palette, which is difficult to obtain directly using k-means. We implement our method using CUDA, and planetary data structure. Please refer to our paper for implementation details about our spatial sampling and visibility computation. The pre-computed palette is then used in our runtime posterization workflow. The existing image posterization method of Chow et al. Uses combinatorial optimization, which is too costly to run in real time when applied to frame-by-frame animation. So in this work, we extend the previous video stylization approach based on bilateral filtering to the palette-based method. Before performing posterization, we pre-compute a palette and a few intermediate colors for predefined step resolution. At runtime, we first iteratively apply a bilateral filter to each rendered frame, and then each pixel color of the filtered image is snapped to one of the pre-computed colors. This way, the final posterization result is represented using the blending of palette colors, which is ready for recoloring. Finally, let me present our results. Thanks to the multi-view consistent palette, our method can produce temporally coherent stylization results. The recoloring is performed by modifying the underlined color. And this is another result of the hot dog model. Please refer to a paper for more results. Our runtime computation is cheap enough to enable real-time interactive application. And this demo application lets users preview, posterize, and recolor the radiance field model. The result is rendered in real time using the planetary data structure. Next, we show the timing analysis of our method. The bottleneck of the palette extraction stage is the radiance sampling, including the computation of visibility for each sample. That said, thanks to our parallel implementation, the whole extraction completes in around 10 seconds. The runtime computation is cheap and typically runs at 30 to 50 FPS. Finally, let's see several comparisons. First is the noise reduction performance. As we've already seen, fitting a convex hull to raw noisy radiance samples produces two vibrant palette colors. The previous optimization-based convex hull refinement approach by Wang et al. Does a better job in noise reduction. But still, color deviations remain in the result as it does not consider visibility. The result of our method has the closest color to the input image in the presence of noisy radiance samples. And this is a side-by-side view. We also test the effect of visibility weight in the k-means-based radiance filtering. The non-weighted k-means method does some job in noise handling. However, there remain unnatural colors like spurious highlights because it does not consider the visibility. Using visibility as weight, our method computes the RGB convex hull, producing a more plausible natural posterization result. And here, let me briefly summarize the presentation. We've introduced palette-based posterization and recoloring workflow tailored to pre-trained volumetric radiance fields. We use volumetric visibility to deal with noise in radiance samples. Our posterization framework runs in real time and enables an interactive application. And of course, our method has several limitations. Currently, we only rely on RGB space geometry to extract the palette. Although our method outperformed baselines, it is not theoretically guaranteed that some reconstruction error metric is minimized in the result. Also, we only consider the stylized color conversion. However, stylization is often performed using different NPR styles in combination. In the future, we plan to investigate optimization-based color editing approaches and ways to incorporate visibility into them. And also, we plan to consider other NPL styles such as feature lines. In this direction, we will further investigate ways to leverage density field information. This is the end of the presentation. Thank you very much for listening.